Hello and welcome back to educator.com and welcome back to biochemistry. So in our last lesson, we closed off by talking about breaking a protein down to elucidate its amino acid sequence. And now we want to go in reverse. What if there's a particular peptide or a protein that I want to build? So today, that's what we're going to be talking about, peptide synthesis. And the process we're going to be talking about is something called the Merrifield process, after Bruce Merrifield, who created this back in the late 60s. Okay, so let's just jump right on in. Okay, so now, let's go, let's use blue. So we're choosing, so we can synthesize small peptides with a sequence of our choosing. So now if there's a particular sequence that I need the peptide, I can actually do it. The sequence of our choosing. And by small, we generally mean up to about 100 amino acids. Up to about 100 amino acids. Can actually do that pretty well. And we also have methods for attaching these fragments to create larger proteins. Fragments to create larger proteins. So before, we took a large protein, we fragmented it, we sequenced the fragments. Now we're just going in reverse. We're creating sequences up to about 100 amino acids long, and then we can take those, let's say, 5 fragments, stick those 5 fragments together, and create a really large protein. This is really, really fantastic. Okay, so what we're going to do, so we'll describe the synthesis of a peptide on a solid support. And I'll tell you what that means in just a second. And this is called the Merrifield peptide synthesis. Okay, so the Merrifield peptide synthesis. So here's the general scheme. Here is the general scheme. Okay. Now this thing that we call a solid support, all these fancy terms, I tell you, you're going to run across all kinds of fancy terms in biology, physics, chemistry, and science in general. And well, I guess they're necessary. I don't know. The part of me always wonders whether they actually are necessary. Why don't they just call things for what they are? But I guess you know how it is. You have to give things certain names. So, okay. So, solid support, it refers to insoluble polymer beads. So just think of really, really, really tiny, small pieces of plastic. That's all it is. So solid support refers to insoluble polymer beads that have reactive chemical groups attached to them. Chemical groups attached to them. And they look like this. So I have this, yeah, I guess I can do this in blue, it's not a problem. So I have this bead, and then in this particular case, the group that I have attached to it, yeah, it's fine. I'll do it down here, CH2Cl. So this is our polymer bead. So this is the bead, and it is insoluble, so it doesn't dissolve. You can actually see it like sand at the, the bottom of a glass of water. And this is our reactive chemical group right here. In this particular case, it happens to be an alkyl halide. Alkyl halide, chlorine, alkyl halide, this chlorine is going to be a good leaving group, chloride, so you can imagine the chemistry is going to take place right here. Some nucleophile is going to come in and it's going to displace the chloride. So this is the reactive chemical group. So basically the chemistry takes place here, and basically this solid support, because we can see it, always see it and keep track of it, we're just going to build the molecule in a long chain all along there. And when we're done, we're just going to pull the beads out, and they're going to have these hairs of peptides. That's all that's happening here. So a solid support refers to the insoluble polymer beads that have reactive chemical groups attached to them. Really, really tiny pieces of plastic that have these chemical groups attached to them, and the reaction can take place. That's it. And because they're insoluble, we can keep track of them. We can filter them. Okay. So what we do is we start with a bead, and just add amino acids one at a time, and just add amino acids extending from the bead. That's it. So basically, let's just take our, we have some bead like that. Well, we add an amino acid, that's one. And then we add another amino acid, and then we add another amino acid, we add another amino acid, we add another we go as long as we want, and we know what sequence we're going in because it's the sequence of our choosing. When we're done, we split this, we break that bond. There we go. We have the protein that we wanted. And because we're actually just adding one at a time, we can always keep track of this because it's insoluble. We see it, we know exactly where it is, and it's very, very easy to deal with. It's a fantastic, fantastic procedure. And in fact, it's fully automated. So you just put the reagents in and you let the machine do your work for you. You come back a day or two later, depending on how long you want your protein to be. It's done. It's ready to go. Okay. Now, okay. In the body, proteins are synthesized. So proteins are built from nitrogen end towards the carbon end. In other words, on a piece of paper, they're built from left to right, from nitrogen to carbon, nitrogen toward carbon. Okay? So in the Merrifield synthesis, it happens in reverse. In the Merrifield process, synthesis is, I wrote the N, the C in the same place, but now I reverse the arrow. It goes from the carbon end to the nitrogen end. So when we build this protein, we're building it from the carbon, we're going to the left, right? Because we're adding this first, and then we're adding something to the left of it, to the left of it, to the left of it, to the left of it. So it's in reverse, but again, the final product is what's important. But you should know that in the body, it's actually built from N forward. You're adding amino acids. Here, you're adding amino acids backward. That's it. You're starting from the carboxyl end, and you're going back that way. Okay. So let's go ahead and illustrate the procedure with an example. We're actually going to build a tripeptide. So let's illustrate the procedure with the synthesis with the synthesis of the tripeptide ala-glycer. So alanine, glycine, serine. So we want to make this tripeptide. How are we going to do it? Okay, well, let's take a look at this. So just some things we want to observe here. So alanine is the N-terminal amino acid. So that's the N-terminus. So serine is the C-terminus, the carboxyl terminus. So we're actually going to be starting with serine, and then we're going to add glycine, and then we're going to add alanine. Because again, in Merrifield synthesis, we move from the carboxyl end towards the nitrogen end, the opposite of what happens in the body. Okay, so what I'm going to do is I'm going to give a general schematic of all the reactions that take place. And then I'm going to go back and I'm going to number these reactions, and then I'm going to go back and go through the details of each of these reactions, including the mechanism. Now, I have to warn you, there's going to be a lot of chemical structures flying around all over the page. But it's really, really important to be able to do this, to understand what's happening at the molecular level, at the atomic level. It's very, very important. It makes all the difference between a marginal understanding and complete command of your material. This is why I'm doing it by hand. And again, this is why I'm not showing you an actual illustration and just going through the illustration, because you have the illustration in your book already, and there are wonderful illustrations in the book, and I absolutely encourage you to look at it, but that's passive. You need to be able to reproduce this. You need to be able to write what's happening. Draw the structure, write the reagent, give the product. That's where full command comes in. Okay. Hopefully I can actually fit this all in one page. If not, it's not a problem. So I'm going to give the general schematic, and again, and then I'm going to go back and go through it in detail. All right, so here is where we start. I'm going to start on the left here. So I'm going to start, remember we said serine. So let me just, where can I put this? I'll put it on top. So again, our peptide we're trying to build is the alanine, glycine, serine. So we want alloglycer. We're going to start with serine, add glycine, then add alanine. Okay, so here's the process. I'm going to take serine and I'm going to react it. Actually, that's fine. I can go a little bit further to the right here. I take serine and I'm going to react it with something called FMOC chloride. And again, this is a general schematic. I'm going to go back and go through all the details. But when I do that, I'm going to end up with FMOC SER. And then I'm going to react this with the bead, and I'm going to end up getting FMOC serine attached to the bead. Okay, then I'm going to react this with trifluoroacetic acid, or mild base. Either one is fine. And I'm going to end up with serine and the bead. Okay, so now over here, I'm going to, so this is going to be reaction number, I'm going to do the reactions in red. This is going to be reaction 1. This is going to be reaction 2. This is going to be reaction 3. Now let me go back to blue. Okay, so over here, now I'm going to deal with the glycine. I'm going to make it ready. So this is going to be coming in this way. So I've got glycine. I'm going to react glycine with my FMOC chloride in order to produce FMOC glycine. And then I'm going to react that with something called DCC. And I'm going to end up producing FMOC gly DCC. Now I'm going to take this, and this is going to be my reagent for this reaction. It's going to come in here, and what's going to end up leaving is DCC. This is going to react with this, and what I'm going to end up with is the following. Let me label some reactions here. This is reaction 4. I'm going to call this one 4A, and I'm going to call this one reaction number 5. And let me go back to blue. So what I end up with is FMOC, gly, ser, and bead. Okay, and again, I subject this to my trifluoroacetic acid or base, mild base, and what I end up with is gly. I really hope I can do this in one page. Ser and bead. And let's go ahead and call this one reaction number 6. I should be able to go one more. Yeah, that's not a problem. Oops. Okay, so now let me go back over here and prepare my alanine. So I'm going to take alanine, and I'm going to react it with this thing called FMOC chloride in order to get FMOC ala. And I'm going to react it with this thing called DCC in order to get FMOC ala DCC. I'm going to take that. That becomes the reagent for this one. DCC leaves the procedure. This is going to react with this. And what I'm going to end up with is the following. I end up with, I have to write it over here, FMOC ala gly ser with a bead. And then I'm going to subject this to trifluoroacetic acid or mild base. And I'm going to end up with let me see, I'm deprotecting. Oh, yes. So I've got ala gly serine bead. And then, of course, I subject this one to hydrofluoric acid, and I'm left with ala, gly, and serine. What it is that I wanted. So this is my general schematic. Let me go through this again, and then I'll go ahead and go through the details. Let me label my reactions. That's reaction 6. This is reaction 7. This is reaction 7A. This is reaction 8. This is reaction 9. And this is reaction 10. I start with my serine. I react it with something called FMOC chloride to create this FMOC protected serine. I react that with a bead. I attach it to the bead. So now I have the bead, a serine residue, and FMOC. React it with trifluoroacetic acid. I take off the FMOC because I need to attach the glycine directly to serine. I prepare my glycine reagent. I take glycine, I protect it with FMOC, and then I add DCC to the right side of it. I take that, I react it with my bead and serine. Now I have my bead, my serine, my glycine, and I have my FMOC. DCC has gone away. I subject that to trifluoroacetic acid. I break off the FMOC, so now I have the glycine that's free to react. I prepare my alanine residue. Alanine, FMOC chloride. This is Cl. To produce FMOC ala. I take the FMOC ala, I react it with DCC to create FMOC ala DCC. I use this reagent to react with the bead serine glycine. Now I have bead serine glycine alanine FMOC. I do TFA to get rid of the FMOC, and then I use hydrofluoric acid to break this thing off the bead. I'm left with my tripeptide. This is the procedure. Notice it goes in cycles. This is why anything that goes in cycles like this, it's perfect for automated procedures. Okay, now we're going to go through each one of these reactions in detail and mechanisms. All right, so here we go. Here's where these structures start to fly around all over the page. Let's hope to God that we can keep this straight. It's actually not that bad. If you can follow this, believe me, you can follow anything. Okay. So our first reaction, let me see, what should I do this in? You know what? I think I'll do these reactions in red. So let me go ahead and do, so we said we started with our serine, right? Okay, so we have H2 N, and we had CC, we had that, and we had O minus. Now our serine is going to be CH2OH. I hope that I got my R group right. I hope that's correct. If not, I hope you'll correct me. Now our first reaction number 1, we reacted this with something called FMOC chloride. This was reaction number 1. And I'll go ahead and write the reaction number in blue. Let me go back to the red, and what we ended up with was FMOC NHCCO minus CH2 and OH. Okay, so let me say what happened here. So we're reacting it with this reagent called FMOC chloride in order to protect the amino group. And here's the reason why we need to protect the amino group. Well, if I take serine, let me do this in black. If I have H2N, or if I take just any random amino acid, notice I have electrons here. This nitrogen is nucleophilic. Well, I have this O minus here. This carboxyl group is also nucleophilic. The next step I'm going to take is I'm going to react this with a bead. Well, the bead is an alkyl halide. Well, since this is a nucleophile and this is a nucleophile, I don't want this to attach to it by accident. I want strictly the carboxyl group to react with the bead end, to react with the bead. I don't want this to react, so I have to protect it. I have to cover it up, keep it from being nucleophilic so that the only nucleophile on this molecule is that. This is why I'm actually reacting it with this FMOC chloride. I'm attaching a protective group so nothing reacts with the nitrogen, right? Because this is nucleophilic, in other words, carrying a negative charge, and this is nucleophilic. I need just that to react with my bead. I don't want this to just randomly react with it, so I have to protect it. That's what's going on. So, I hope that made sense. Okay. Now let's go ahead and draw the structure for FMOC chloride, just so you see what it looks like, but I'm just going to refer to it as FMOC chloride. And it looks like this. We have that, and then we have another one, and then of course we have this, then we have CH2, COCl. Okay, so this is an acid chloride. It's a carbonyl chloride. Okay, this chloride is going to be your leaving group. Sorry, let me go ahead and put my aromatic, because this is definitely aromatic. Okay, so this right here, that's the FMOC part. And of course, this is the chloride. So just so you know, this stands for 9-fluorenyl methoxycarbonyl. All these names. Methoxycarbonyl. Chloride. 9-fluorenyl. Wait. I think I have my structure wrong here. Ah, well, it doesn't matter. We're only concerned with the FMOC chloride. This is what we're concerned with right here. I think I'm missing an oxygen here somewhere, but that's okay. Again, FMOC chloride, it's the chloride part that we're concerned with. This is where the reaction is going to take place. We're just going to call this FMOC. It's just a protecting group. And here's how it happens. The mechanism is these electrons they attack that carbon and they kick off a chloride. So now you have this FMOC group attached to the nitrogen. That's how it ends up attached to the nitrogen. And this is our final product. Okay. There we go. Great. So now we have an N protected serine. Okay, so we have our, let me go ahead and, yeah, that's fine. Let me go ahead and do this in red. So let's take our FMOC, and let's take our serine, NCC. So that's our serine. Now let's go ahead and do reaction number 2. Should I do it vertically or should I do it, that's fine, I guess I can do it this way. Actually, let me go ahead and do it this way. Now, I'm going to react this with the bead, and I'm going to actually draw out the bead here. Boom, 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 boom here. That's that. We have CH2, we have Cl, and here's what happens. So this is going to be reaction number 2. Let me erase something here and do this over. It's not going to, so let me go. All right, let me put my H2s down here, and then let me go ahead and do my blue. So the mechanism is this nucleophilic oxygen attacks that carbon, and it kicks off that. So what ends up leaving here is our chloride. So this reagent attacks the bead, and now it's going to be attached to the bead. So now what we have is the following. We have, let me go back to red. I have FMOC, I have N, CC, this is carbonyl, this is O, and this is, I'm just going to write bead, okay? And this is our serine, so this is CH2, this is OH, and let me go ahead and put my H there. So N-protected serine, I reacted with a bead, now I have bead, serine, and I have FMOC. There we go. Now I'm going to go ahead and react this with, so this is going to be reaction number 3. Go back to red. This is going to be our trifluoroacetic acid or our mild base, and this is to take off the FMOC group to deprotect the nitrogen. So what I end up with is the following. I end up with, let me just write it as H2N, C, C, there's that, oops, there's no minus there. I'm actually attached to the bead. Let me see, yes, attached to the bead. And then of course I have my CH2 and I have my OH. There you go. So now I have the bead and I have my serine. So this is my serine residue, and that is the third reaction. Okay. Now, let's go ahead and deal with our fourth reaction and our 4A reaction, the preparation of glycine. So let me go back to red. So let me go ahead and draw out the, so we have H2N, this is CC, this is O minus, and of course glycine has just a hydrogen there. So this is glycine. Now what I'm doing is I'm reacting this again with my FMOC chloride to create my N-protected glycine. This is going to produce FMOC, NCC. I have that. This is glycine. There is an H there. Okay, this is my N-protected glycine residue. Now I'm going to subject that to my DCC, dicyclohexyl carbodiimide. And I'll discuss this in just a minute. Let me go ahead and draw the structure. When I react it with my DCC, I end up with the following. I end up with FMOC on the left. I end up with my amino acid on the right. ODCC, and I end up with a DCC on the right attached to the amino acid. This is glycine. I'll go ahead and put an H here. So I have FMOC, I have my glycine, and I have my DCC. I've prepared my reagent to react with what's on the bead. So let me go ahead and write the fact that this is glycine. And now let me start talking about what is going on here. So let me draw the structure of DCC, and then I'll show you the mechanism going from this step to this step. So the mechanism from here to here is, again, this nitrogen. It attacks the FMOC, and it kicks off the chloride. So chloride actually goes away. This is reaction number 4. This is reaction 4A. So now what happens is this. So now let me go ahead and draw dicyclohexyl carbodiimide. That's fine. I guess I can draw it here. This is N, double bonded with a C, double bonded with an N, and another cyclohexyl group, something like that. Okay, so I'm going to go ahead and put just a floating H, not yet. Okay, so this is DCC. DCC. This is called dicyclohexyl carbodiimide. We'll just call it DCC. Once I've created my N-protected glycine, now this is no longer nucleophilic. That's why I protected it. This is going to be nucleophilic. It's going to, let me do my mechanisms in blue, actually. This is going to attack that carbon. And of course, we're pushing electrons, so it's going to push this out towards grabbing some H. And what you end up with, so now I'm going to draw this structure with this thing attached. It is going to be, let me do it in red, just so you see it. I'm actually just going to be writing FMOC, amino acid, and DCC, but I wanted you to see the picture because, again, this is biochemistry, and it's all about the chemistry, the organic chemistry, the structures. N, C, C, this goes there. This is O, this is going to be C, this is going to be N, H, cyclohexyl, this is going to be N, and this is going to be a cyclohexyl. So this DCC, that is this thing right here. That's that. So that's it. So now we have this reagent. Now we're ready to go through and do reaction number 5. Okay. Do I have 4? 4A, everything is good. Yes, everything is good. Okay. So now, let's see what we've got. So we have our serine attached to the bead. So let's go ahead and do that. Now let's go to red because that's what we're doing our reaction in. So we have H2N, C, C, that's a carbonyl, that's O, this is CH2, I'm just going to write bead. O, and this is the bead. This is CH2. This is OH. Okay, so this reaction that takes place is going to be the following. Should I go straight down? Oh, yeah, that's fine. I can go straight down. I'm going to react it with the reagent that I just made. I'm going to react it with the FMOC, NCC, O, DCC, our glycine, right? So here's how this one works. Now, mechanisms we do in blue. These electrons, that's nucleophilic. That's going to come around. It's going to attack this carbonyl because it is electrophilic. These electrons are going to pop up here. It's going to form a tetrahedral intermediate. Then the electrons are going to pop back down here, and they're going to kick off this DCCO group. So our final product, what you end up with, is the following. You end up with this thing on the left of this thing. So our final product is going to be FMOC, NCC, and then NCC, carbonyl, carbonyl, O. This is attached to the bead. This is there. This is our glycine. This is there. This is our serine, CH2OH. This is what I've made. Now I have my serine, and I have my glycine to the left of it. That's what I've done. Okay. Now let's stop and take a look at where we are just to make sure we've got everything. Okay, let's go ahead and label some reactions. This is reaction number 5. And of course, the thing that ends up leaving from this reaction is DCC because that's our leaving group. Now what we do, we're going to subject this to trifluoroacetic acid or mild base in order to deprotect, to take off this FMOC group. So what I'm left with now is my glycine residue, my serine residue attached to my bead. So I've got H2NCC, NCC. I have a carbonyl on the second carbon, carbonyl on the second carbon. This is attached to our bead covalently. I'm going to go ahead and put that there. I'm going to go ahead and put an H there. Now I'll go ahead and do my R groups. This is glycine, and this is CH2OH. That is my serine. I have my bead, my serine, my glycine. Now I'm ready to start the next process. This reaction was reaction number 6 in our general scheme. Okay, we're almost there. We're more than halfway through. Now we have to prepare the alanine in order to have it react with this thing and attach it to the bead. And that's going to be our last amino acid. So let's go ahead and do that. So let's take alanine. Let's go ahead and do it in, no, let's go ahead and do it in black, actually. So we've got H2N, C, C. So we take our alanine, which is CH3. We react it with FMOC chloride. And again, let's go ahead and do the mechanism in blue. This nitrogen is nucleophilic. It will attach that. It will kick that off. Chloride leaves. This is reaction 7. And what we end up forming, let me go back to black, is our FMOC protected alanine residue. NCCO-. I'll go ahead and attach an H, and this is alanine, so this is CH3. We go ahead and activate the carboxyl by reacting it with our DCC. So now I go this way and I react it with DCC. This is reaction 7A. And when I do this, what I end up with is the following reagent. FMOC, N, C, C. This is H. This is carbonyl. This is O. This is our DCC. And this is alanine. So this is CH3. So we have this alanine. FMOC, alanine, DCC. This is ready for the next step. So now let's go to reaction number 8. Okay. Reaction number 8. So now we have our bead. Our bead has a serine and then a glycine. We're going to react that with the reagent we just produced, the alanine reagent. So let me go to red. So I've got H2NCC, NCC, NCC. There's a carbonyl here. There's a carbonyl here. There is an O, and there is a bead. Our first residue is serine. That is there. Our second residue is glycine, and I have these electrons on the nitrogen. So what I'm going to do now, I'm going to react this with my, let me write this in black, the reagent that I just produced, which is, nope, I said we're going to do this in black. Let's hope this cooperates. Yes, there we go. I have FMOC. I have N. I have C. I have C. O. DCC. This is H. This is my alanine reagent, right? This is my alanine reagent. I'm going to stop writing this down. Alanine reagent. When it reacts with that, DCC actually leaves. This reaction is reaction number 8, and here is the mechanism. Let me see, where are we? Yes. Yes, here we go. I have blue ink. I'm telling you, this gets kind of crazy trying to keep track of everything, but this is actually the nice part, taking the time to keep track of everything, to be able to know where you are, to search through all of this chemical jungle that we're looking through, to actually make sure you know exactly which electrons are going where. This is where you have a complete understanding of the material. So these electrons come here, they attack that, these electrons go there, they fall back down, they kick off the DCO leaving group, and what you end up with is the following. Let me write this in red. You end up with FMOC, NCC, 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 carbonyl, carbonyl. Those are my points of reference, my carbonyls. I have my O, I have my bead. My first residue on the bead is my serine, CH2OH. My second is my glycine, which is just H. My third is my alanine, which is CH3. There is a hydrogen attached to the nitrogen, a hydrogen attached to the nitrogen, a hydrogen attached to the nitrogen. There you go. I've got my serine. Sorry, I'm not going to actually do this. I've got my bead, serine residue, glycine residue, alanine residue, and now it's protected. Now I need to deprotect it and break it off of the bead. That's it. Reactions 9 and 10. So now I'm going to do these as single arrows. Let me go ahead. This first step is going to be the trifluoroacetic acid. This is reaction 9, or mild base. To remove the FMOC. Once I remove the FMOC, now my number 10 reaction, I'm going to react it with hydrofluoric acid to remove the bead. Or actually, because that's the solid support, I'm going to remove the peptide from the bead. And what I end up with is exactly what I wanted. And this one I'm going to do in blue. I end up with alanine, glycine. I never, ever get that right. Okay, and serine. Serine is my C terminus. Alanine is my N terminus. That's it. I've just run through the Merrifield process with mechanism, with structure. I've kept it as FMOC, I've kept it as bead, in order to concentrate just on the structure of this, but running through the same thing. You protect the nitrogen group. You add an amino acid to the bead. You prepare the next group. You protect the nitrogen group. You activate the carboxyl group with the DCC. You react these two. Now you have something else on the bead. You deprotect the nitrogen group, prepare it. You prepare your third amino acid. React it, protect the nitrogen group, activate the carboxyl group, react it. Now you've added one more chain. Deprotect the nitrogen, prepare it, go to your fourth amino acid over and over and over again. That's the Merrifield synthesis. It is an automated procedure. Now what I'd like to do is like to actually go ahead and show you how this takes place physically, as far as the reaction vessel that it actually takes place in. So let me go ahead and just go forward to my picture here. Aha, okay. So this is a chromatography column. Now you can do this on a chromatography column, or you can also do it by hand by just having a, well, you know what, let's just deal with the chromatography column. So this stationary phase right here, these are our beads. So basically what you're looking at is just imagine a bunch of really tiny beads. That's it. So you've got hundreds and hundreds and hundreds of thousands of beads. So that's it. It's like sand basically. It's just like really finely ground sand is what it is. So you take this column, this chromatography column, which is just a hollow tube, comes in different sizes. It could be really thin. It could be really thick. Generally, they tend to be pretty small for the Merrifield synthesis. And you just fill it up. So you just fill it up with a bunch of beads. Well, you remember the process that you went through, the schematic. So let me go back to the schematic. And so now, because you're actually constructing this molecule, this peptide, on a solid support, all of your solutions, you just pour them in. The reaction takes place as it filters through and passes through the beads, and then it exits when you want it to exit. And of course, you can control the flow down here. So that's it. So for example, you create your serine and you react it with FMOC chloride, right? So you create your N-protected serine residue. Well, now you're going to react it with a bead. Well, the bead's already in the column. So what you do is you take that solution and you just pour it through. So that's going to be reaction number 2. And it's going to go ahead and react, and everything, the serine is going to stick to the bead, and everything else is just going to wash through. That's what makes this great. You don't have to purify anything. All the excess reagents, everything that you don't need, just washes through. You can throw it away. Well, now you go ahead and you pour in your trifluoroacetic acid or your mild base to deprotect. Again, the reaction will take place as it passes over all of the beads, and any excess will run off. Now you go ahead and you create your glycine reagent. You pour it in here. It'll react as it passes over the bead. Any excess will run off. You put your trifluoroacetic acid. It'll run over the beads, and that's what you're doing. Stationary phase. It doesn't move. You're literally just washing all of the beads with all of the reagents that you need. The beads just stay there. The reaction takes place on the bead. When you're done, you take the column, you empty out the beads. Actually, no, you don't even have to do that. The final step, the hydrofluoric acid, you just pour it in. The hydrofluoric acid runs over the beads. It breaks the bond between the bead and the first peptide, and then of course you just wash it into a flask, and now you have your peptide in a flask down here for further processing. That is the Merrifield synthesis. Thank you very much for joining us here at educator.com. We'll see you next time. Bye-bye.